it's looking at any string coming in. Alright. Now this G here, but you may ask me, what's the point? The point to note is this G here is the grammar of this language. That's the critical point, I think, because because the whole point of this machine is to decide any element that belongs to this language can be generated by this language's grammar. But that's what S is checking. Okay, that's what S does. S checks that this grammar can generate that that string, and the Turing machine S will return. It will accept or reject that question, and then putting that ability inside this bigger thing, you're then able to show whether a random string belongs to this language or not. That's something else, right? Whether W belongs to A is a different thing from whether this grammar can generate that W. I hope you appreciate that, right? It's sort of important. Alright, so that's it. Alright, now finish off this section, because it's about to start, ta-da! I'll give a real trumpet roll when we get into it. So a bit of a comment. This theorem, 4.9, that's in a sense the final link, the final piece in a discussion of 4 kinds of languages that we've been trying to show are decidable and such things. So we've been describing 4 classes. He always uses that term. Maybe he's trying to avoid the term set. See, for historical reasons, you go back a century or so, Bertrand Russell and others were saying all kinds of paradoxes come from when you're taking sets of sets, and when sets can include themselves as members, you get all sorts of nutty things. So I think it was Russell who's to avoid such paradoxical conclusions and self-contradictory. The Barber paradox. I think I've mentioned that before. I'll just mention it quickly. There's an island somewhere, and all the men on that island, they have 2 options when it comes to shaving. They can either shave themselves, which a lot do, and some prefer to go to the barber to be shaved. Okay, nothing complicated about that. The problem comes with the barber, and let's say there's a law on this island that the barber he's only allowed by law to shave people who don't shave themselves. Okay, so all those guys who don't shave themselves, they come to the barber to be shaved. The problem arises, well, who shaves the barber? Right? No, I won't. I won't give you the answer. I'll just let you think about it, because it's sort of interesting. But I'll give you the conclusion, but you can fill in the logic yourself. If the barber shaves himself, therefore he does not shave himself. If the barber does not shave himself, therefore he shaves himself. And just flatly self-contradictory. Right? You've got a problem, and there are lots of problems like that. So Russell, in his tome, Principia Logica or Mathematica, he wrote this long tome trying to prove that mathematics can be derived from set theory. And to avoid these paradoxes, he introduced the notion of class rather than set. And a class, I think we're not allowed to have members that where the members was the same set. So a class, I think, is I'm not too sure, I'm a bit rusty. I haven't studied Russell's stuff, but I think a class is a set where it is not allowed for that set to have a member that is itself. Something like that. So maybe that's why Sipser is using this word class a lot rather than just the set. Anyway, okay, so classes of language, or rather 4 main sets of languages that we've been talking about so far. So the regular languages, that was what Chapter 1 was all about, and context-free languages, that's what Chapter 2 was all about. And this chapter we've been talking a lot about decidable languages, meaning you have Turing machines that accept all the members of the language and reject all other strings. And another class of language, Turing recognizable. Now, we haven't talked a lot about that, but well, we've mentioned it a couple of times in passing. I'll just mention it again. You want your memory refreshed. Turing recognizable, what does that mean? It means that if a string is a member of a language or a set, then there is a Turing machine that can accept that string, but may not be able to reject other strings that are not a member of the language. Because if the Turing machine is not a decider, well, that means it might be a looper, what I'm starting to call a looper. That means the Turing machine might never halt, right? It loops, by definition. To loop means to not halt. And it just goes on forever. So a Turing recognizable machine, another Turing machine, would accept the members of that language, the Turing recognizable languages of that language, but it might turn out to be a looping machine when it comes to strings that are not member of that language. Right? So that Turing machine is not deciding. So now there are more languages. This is a broader category of languages than this category, okay? And that in turn is a broader category of languages than this one, and that in turn is a broader category of language than this one. Or turning it around the other way, the set or class of languages that are regular, that's a subset of the class of languages that are context-free, which in turn is a subset of the languages which are decidable, which is a subset of the languages which are Turing recognizable. Right? So now we've got like four levels of Venn diagram. Right? Right? This is a subset of that, this is a subset of that, and this is a subset of that. So this and this are subsets of that, and so forth. Okay. Ta-da! Da-da-da-da! Da-da-da! Section 4.2, the highlight not only of this course, but I would say, and a lot of people would agree with me, the very highlight of the whole of the theory of computation. Right? A big moment, a dramatic moment. The highlight of the course and theory of computation. 5 exclamation marks, which is about my limit. Right? So here I put 3. Okay. Now in this section we prove one of the most philosophically important theorems in the theory of computation. That is, there's a specific problem that is algorithmically unsolvable, underlined 3 times. What that's saying is that there are some problems that you can find no algorithm for, no Turing machine that can decide, give a yes or no answer to that question. Some things are just undecidable, unsolvable, provably unsolvable. Keep saying, what a concept. Proving that something is impossible to solve. My brain still sort of jolts at that very notion. Provable unsolvability. If that doesn't shock you, who was it who said? There's a famous physicist called Niels Bohr, and he was saying about quantum mechanics, a similar feeling I'm expressing right now, that, and here's his famous quote about quantum mechanics: anyone who is not shocked by quantum mechanics has not understood it. Okay? So I guess I'm saying something similar about this. If you are not shocked by the very notion, the very concept of provable unsolvability, then either you're a lot brighter than I am and you've seen things I've not seen, or the reverse. Okay, you're not seeing how weird that is. How, well, I don't know, perhaps I should shut up and just say and restrict my opinions to myself. But I find that concept truly weird, amazing, jaw-dropping, incredible, philosophically profound, provable unsolvability. Wow. I'm speechless. Alright, next session.